Hello, welcome to another wonderful episode of the New York City Category Theory Seminar. And this week we have Joseph Dorfer from the University from Austria, from the University of Graz, and he's going to talk about NP-completeness of finding shortest combinatorial paths in the Associahedron. Hold on, I just want to point out it was Peter Hines who joined us. Hello, Peter. Who pointed this paper out to me, and I thought it was fascinating. And Joseph is a newcomer to category theory. He's a combinatorialist or complexity theorist, whatever, and he's we welcome him with open arms. Okay, take it away.
Then thanks for the warm welcome and thanks for the invitation to give this talk today. So I'll start off. Sorry, I just realized my microphone was off.
Oh,
Yeah, thanks for the
we
warm
hear
welcome.
you perfectly.
Okay. All right, thanks. Then I'll start right away. With the very basics. So this right here is a convex polygon. We have our vertices equally spaced on a circle, and yeah, every connecting line between two vertices of the polygon is entirely contained in the polygon. And what we can do now is triangulate this polygon, so decompose it into many triangles. And we can modify these triangulations via flips. So what are the details here? Whenever we have such a convex quadrilateral composed of two triangles and joined by one such diagonal edge, then we can perform a flip in which we remove this one diagonal through the quadrilateral and we add the second diagonal of the quadrilateral. So that's a flip. And with this notion of a flip, we can define a flip graph. This is a metagraph of triangulations where we have a vertex for every triangulation of a convex polygon. And we have an edge between two vertices if these corresponding triangulations can be transformed into one another via a single flip. And if we continue this for all possible triangulations, in this case of the hexagon, then we get this nice graph right here, and I have already drawn it as a convex polytope. And actually, this is quite a famous polytope because the flip graph of triangulations corresponds to the one skeleton of the famous Associahedron.
Joseph,
Yeah.
could you just do me a favor? Back up. Could you just
Yeah.
go through the first upper right edge? I don't see where you have the flip.
First,
Right, from there to there, from there to the one on the
from there
right.
to there,
Right. Could you
between
just
those two.
right.
So if we look at this at the four vertices up here and
Yeah.
this one diagonal, if we flip it, we get this other
Oh,
diagonal, and that's
I see.
exactly
Okay.
this one.
Okay. Thank you. Thank you. Got it. Okay. Fine.
Yeah,
Perfect.
thanks. Yeah, please just ask if there are any questions. I'm happy to clarify anything.
Okay. We're going to call a flip
Um,
a reassociation. Okay,
okay.
but fine. That's fine.
Yeah, thanks that you mentioned a different name for flips, because actually this slide is about introducing many different names about of flips, because we have the triangulations here, and triangulations of convex polygons are Catalan structures, and so are binary trees. So we can go from triangulations to binary trees. If we look at this dual graph, we connect, we have a vertex for every edge, and we connect two vertices if the edges belong to the same triangle and go further away from the root. So we have binary trees, and probably with reassociations, we can also go from binary trees to bracketings, or I have been told that this sometimes is called associations. So how is the projection here? Every internal node just puts parentheses around its two children, and I've denoted the children with start here. So the first round is this, so always one pair of parentheses around the two children. And on the next level, we just put parentheses around the next, around the children. And if we continue this, we get this, bracketing or parenthesization, or probably for you, the preferred name, I guess, is then association. Yeah. And we have the flip here. And this also has a nice interpretation in the other structures with the binary trees, for example. This is a rotation exchanging a vertex with its parent and reattaching the children such that we preserve the labeling in an increasing way, or applying the associativity rule to the brackets and moving one pair of brackets to a different position. And now to come to the lead question of my talk, this goes back to 1982 when Culik and Wood asked if we have, so they asked it in terms of binary trees, but actually we could have asked it for triangulations or associations. If we have two binary trees, how hard, so what is the complexity of finding the minimum numbers of rotations to go from one such binary tree to another? And probably when phrasing it in terms of binary trees, this comes with the computer scientific motivation, with binary trees as search structures. So we have this collection of some numbers, and we want to find some element in here, for example, the 12, and we don't want to look at all numbers. So what we do is, when storing these numbers, we store them in a tree structure such that for every child, for every vertex, the entries in the left child are smaller and the entries in the right child get larger. And then finding something becomes pretty easy. So the 12 is larger than the 11, so we look to the right. It's smaller than the 43, so we look to the left. Again, smaller than 25, go left. Smaller than 13, go left. And we found the 12. And we only had to look at 5 entries instead of looking at the whole tree. So that's nice when, for computer scientists, when storing data, that we can find things that we previously stored quickly without having to look at everything that's in there. But it turns out some trees are better suited for this than others. So if we look for some element at the very bottom of this tree, this may again take very long. So again, the message is some binary trees are better for searching than others. And what we want to do is transform one of the trees, like one of these poorly suited trees, in one of the better suited trees using rotations. So that's the motivation why we want to transform spanning trees, not spanning trees, sorry, binary trees into one another. And now, how do we answer this question? So the term complexity of determining something shows up, and I've decided to present the possible answers as well by giving a short introductions to the very fundamental terms of complexity theory with P, NP, and NP-completeness. So I'll start with the middle one with NP problems. And here we have a nice definition. So NP is the class of decision problems for which there exists a deterministic polynomial time Turing machine and called a verifier and a polynomial. Yeah, you don't need to know this formal stuff. For us, so I asked ChatGPT to simplify this like M5, and what came back was this definition right here, which is good enough for our purposes. NP is the set of decision problems where if someone else gives you a solution, you can check on your own really quickly whether this really verifies the decision problem or not. And then a colleague pointed out to me that this really quickly is a very bad simplification, and I should mention that this means in the time steps that it takes to verify grows bounded by some polynomial. And let's start with some examples that fit into this topic. We start with the Associahedron, and how would a suited decision problem look here? We start with two triangulations. So the problem has as an input two triangulations t and t prime and an integer k. And the question is, can we transform one triangulation into the other using at most k flips? Here's an example, one triangulation and the other, and let's say k is equal to 5. And now I'm this someone who gives you a solution, for example, this one. And now it's the task is to verify efficiently whether this is a good solution. And we can do this by checking that every transformation step is indeed a valid flip. And in the end, we transformed t to t prime using at most 5 flips. So we can efficiently verify that my solution that I just presented is indeed a solution to answer this question above with yes. So proof by example, this is indeed an NP problem. If we want to prove this more formally, what we need there is that the diameter of the Associahedron is bounded by some polynomial, such that indeed these steps, we indeed only have polynomially many steps, such that this doesn't take too long.
So let me just
Okay.
So there's for an n-ary polygon, there's a exponential amount of edges. I'm sorry, there's an exponential amount of
In the
vertices.
Associahedron,
Yes.
yes, the Associahedron has an exponential number of vertices, but we can reach any vertex from any other in at most 2n minus 10 steps for n reasonably large.
So there's an exponential amount of, so there's an exponential amount of edges, and the most distance are everything reassociated to the left and everything reassociated to the right.
The most distant, that's this Purneur, this paper by Lionel Purneur, where he gave these zigzag triangulations with small fans at the end and shifted them slightly. And for those, it takes 2n minus 6. So for an n-gon, 2n minus 10 flips to go from one to the other. And that's provably the worst
The
possible,
longest, the
the longest path that can occur. So
2n, not,
actually, so
yeah.
yeah. So those I call them fan triangulations, where everything is attached to one vertex, are actually pretty nice because in every step we can find one edge that we can flip such that it is then attached to this vertex, and we can increase the number of edges incident to that vertex by one in every iteration. So those are actually, for finding flip sequences, those star triangulations are actually, or fan triangulations are actually pretty nice.
And they don't
So
correspond
these zigzag paths are the mean ones. Sorry?
they don't correspond to all the parentheses on one side, or not. I think they do. Well, let me put it this way.
These
All the
fans do,
parentheses on
yeah.
one side correspond to a fan polygon, but there's obviously
Probably yes, yeah.
there's n minus one fan polygons. This,
Yes,
so only two of them are extreme parentizations. Okay, anyways, good, fine. It's
yes,
an NP problem. Perfect. Go on. Sorry.
yeah. Um, yeah, then the second example, um, having the Permutohedron, and there the elements are permutations. And we can again ask, if we have two permutations, can we transform one into the other using at most k transposition steps? And I use the edges as transposition of two consecutive elements. I know sometimes the inverse is used, but I think for this illustration purpose, using transpositions of consecutive elements is the easier way to go. And again, an example, two permutations and an integer k, again 5. And again, I can give you some solution and you can check that every step is a valid transposition. But counting the number of transpositions, it turns out that this is more than this bound of 5 that we gave. So this solution right here is not a certificate for this question up there to be answered with yes. Another example of what would not be a suitable certificate is this one, because, well, it's shorter, it's only 2 steps, but the second step is not a valid transposition. So we have seen a different example for something that is not a certificate. But again, there is some example for something that is a certificate. And here we could really check every step is a valid transposition, and it's 1, 2, 3, 4 steps in this case. So we can verify the question up there for these two permutations, and this k equals 5 can be answered with yes. So again, proof by example, this is an NP problem up there. And the last example that I chose is the hypercube.
Joseph, could you just go back for a second?
Yeah.
Let's just do a similar analysis. You have n factorial vertices here.
Yes.
So that's worse than exponential. And what's the largest distance you can have between any two of them?
I was going to put it on a later slide. So
Oh, okay. No. So
actually
fine, it's fine.
counting in, so you can count inversions. So going from the totally sorted permutation to the sorted in an opposite way permutation, that then you have see that every entry needs to jump over all other entries at some point, and this gives somewhat n choose 2, so order of n squared many steps.
And
So
choose
the
to,
maximum distance.
fine. Okay, perfect. But it's not exponential. Okay, fine.
And for the last one, the hypercube, vertices are strings of zeros and ones. And what is the how are the edges defined? It's just the exchange of one. In one position, we can exchange a 0 with a 1 or 1 with a 0. And let's ask for these two strings of 0 and 1, zeros and ones, and k equals 6. Is there a sequence of 6 steps that transforms this one on top to the one at the bottom? Again, I could give you this solution right here, and you could again try to verify and find out, well, that's 8 steps, so that's too long. But not only that, you can find these 2 steps. We have a 0 going to a 1 going to a 0. Those 2 steps were not necessary. We are changing something from 0 to 1 and back. We don't need that. So actually, you don't need me to give you a solution. You can come up with some optimal solution that doesn't do these unnecessary steps yourself. And that's how I'm going to introduce the other problem class P. So for polynomial, recall for NP we had, if someone else gives you a solution, you can efficiently check whether it's a feasible solution for your decision problem. And actually, P is then the class where you can come up with these solutions yourself. And yeah, again, a colleague pointed out that this really quickly might be misleading. Yeah, now going back to the hypercube, that's a problem in P because the distance between two strings you can compute on your own. It's just the number of positions in which the starting string and the end string differ. So if we have a 0 in one and a 1 in the other, then we need to swap it at some point, and that's just the distance here. And
I think that's called the
briefly,
Hammond. It's called the
yeah,
Hammond distance or Hamming something. Okay,
Yeah, Hamming.
yeah.
thank you.
And for the Permutohedron, there's also such a formula. It's a little bit more hidden, but what we can do is we can relabel the elements of the second permutation such that it is just the sorted one going from 1 all the way up. And if we relabel the elements in both the start and end permutation, then the distance is just given by the number of inversions. So entries I and j, where I is less than j, but the entry in position I is larger than the entry in position j, and this prime right here is one too much. So it should be p in both cases. So all we have to do is compare all two entries and check whether they are already in right order or inverted. And every such step is one inversion that we have to overcome at some point, and this gives us the distance. And with this we have seen, and from this it's now easier to see the maximum distance between two permutations is the one that maximizes the number of inversions. And that's the case if one is the sorted permutation and the other one is the inverse sorted permutation. Yeah, so we have seen there's problems that we can solve efficiently ourselves. There's the hypercube, the Permutohedron. There's problems where we can check a solution if someone else gives it to us. Where in these two areas do we place the Associahedron? Is it here in this green area, or is it in this red area outside here? And let's go even one step further. I've got a screenshot from the Wikipedia article on millennium problems here. It's actually a very big open problem whether there even exists a problem for which we can verify solutions efficiently, but not come up with them efficiently ourselves. Okay, it's really small right here. It says most mathematicians and computer scientists expect that these two sets are not the same, but it remains a big open question worth $1 million. So, yeah. And how is this problem motivated? How did this really come up, this P versus NP problem? It came up in the 70s with this theorem that says Boolean satisfiability is NP complete. So again, many terms to explain. Boolean satisfiability asks if we have such a Boolean formula like this one right here, is there an assignment to the variables such that the formula in the end evaluates to 1? So for every variable, we can put 0 or 1, and just evaluating with known deduction rules, is there one way to assign zeros and ones here such that in the end we end up with a 1? This problem is contained in NP because if I give you some assignment to the variables, what you can do is plug them all in, evaluate the formulas, and say, yes, this evaluates to 1, or no, it doesn't. And the big part of this theorem is this problem is at least as hard as all other problems in NP. So every NP problem can be written as some reasonably sized Boolean formula. And if we can solve this Boolean satisfiability problem efficiently, then actually we can solve all other NP problems also efficiently. And therefore, in this diagram from before, these two sets P and NP would be the same. And this is where my result comes into play. What I have shown is that the flip distance of triangulations of convex polygons is NP complete. So again, what does this mean? If we can solve this flip distance problem efficiently, then actually we can solve every NP problem efficiently. And how do we prove something like this? The way we are going to do this is we are going to solve Boolean formulas, so this original NP-complete problem, by using flip sequences between triangulations of convex polygons. Um, yeah, this is probably the most technical slide that I have prepared. With this, we are going to solve Boolean formulas using flip sequences. Should say we are going to approximately solve some Boolean formulas, because in the last 50 years or so, there has been some progress towards which Boolean formulas do we have to solve and which we don't. And actually, those formulas that we have to solve got much simpler over the years. So with all the adjectives right here, the variant we are looking at is planar, monotone, separable, max 2-sat, which says we have to solve formulas of the following form that we have right here. We have these clauses where we have two variables that are connected by this OR operator, and these two variables or literals that show up either both represent a positive assignment to a variable or both represent a negative assignment to a variable. And all those clauses are connected via AND operators. And there's some parts additionally. If we have this variable clause incident graph that connects, that has variables and clauses as vertices and connects variables with clauses whenever a variable is contained in a clause, then this graph can be drawn in this nice representation with variables on a horizontal line and clauses above and below this horizontal line, and the clauses that we have above are exactly the clauses that have positive literals in them, and the clauses at the bottom are exactly the ones with the negative literals in them. And now I'm almost done.
Joseph, 1 second.
Yeah.
I thought it's known that 2-sat is P, is in P.
Correct. 2-sat is in P, but max 2-sat, so where we know that we can't actually fulfill the whole formula, but we're just trying to satisfy as many clauses as possible. That's hard again.
Okay, so
we are solving
1 second.
this maximization version.
So max 2-sat, you're given a formula with two clauses, and you're given a number k, and you want to know, can you satisfy k of them?
Yes. So not necessary. So definitely not all of them, because just all of them or not all of them, that's in P. You're correct. But if this k is in some suitable range, then it's actually hard to see that, to efficiently determine whether it's more than k or less than k. But
Okay.
yeah, great catch. The version without the maximization would be in P.
Okay. Are you going to, the planar, I assume planar means that the picture can be drawn, the picture that you drew on the right, on the left, can be drawn on a plain piece of paper.
Exactly. So as we
And
see here, none
monotone,
of these.
monotone means they're all positives or all negatives.
Yes.
And what does separable mean?
That you can separate the positive clauses on top from the negative clauses at the bottom with this nice horizontal line going through it.
It's hard to see where you couldn't do such a thing. Okay.
Well, you couldn't if your formula wasn't one of these formulas, right? If it was a general
Yes.
Boolean formula, not one of these things that made out of disjunctions of pairs.
No, but he's saying that even if you have disjunctions of pairs and all of them are positive or negative, there's another thing called separable. I just don't see what that is.
Okay.
Okay, but fine. It's Joseph, it's not important. Go on.
Okay, and here's the steps of the proof. So from this formula with this nice drawing, we are constructing two triangulations. And if we have some flip sequence, some short flip sequence between those two triangulations, what we get from them is a good truth assignment for uh, for our for our original two-sat formula. So the shorter this flip sequence, the more clauses we can satisfy there, and it's actually an equivalence. So if there is just no good flip sequence, then this is because there's also no good truth assignment for this formula over here. So these are the steps, and now how do we construct these triangulations? There's With this nice representation that we have up here, there's actually just two building blocks. We somehow need to build variables, and we need to build these two clauses. And let's see how this is done. And okay, one more technical slide, because this helps when building something and then putting everything together into a triangulation of a convex polygon. I have introduced these convex polygons as points that are equally spaced on a circle. A different way to draw this is with the points all on a horizontal line. We have the edges that were previously on the boundary are now almost all on this horizontal spine, except for the one where we unfold the entire thing. That's now the long one going on top. And we draw all the edges except for the ones on the spine as semicircles, like the 1, 7. Here again, just as a semicircle. 8, 12 also. 8 to 12 is going here. So it's really the same triangulation, just represented in a different way. And in a flip sequence, there's not one triangulation, but there's at least two, the one that we start with and the one that we want to finish with. And we use this, and we use the convention that we draw the triangulation that we start with on top and the other one at the bottom. And this is helpful because we also have this nice representation of the two-sat formula. So in both we have this spine, ones with the variables and ones with the vertices, and we have something going on the top and something going on at the bottom. And it's the same for the triangulations. We have the vertices on the spine, we have the starting triangulation on the top, and the one that we finish with on the bottom. So we use this so these similarities between these two representations are really helpful for our building steps. Okay, now to the individual building steps. We have this variable right here in the two-sat formula, and we have this. I gave you this pair of triangulations right here, and you see this pair of triangulations, but what I see is actually a way to encode a variable right here. So the first thing I want you to see is at some point we want to add these edges from the target triangulation to the original triangulation. And we see these edges are crossed a lot of times. So at least half of the starting edges all cross the target edges. So we can't immediately start adding the target edges. We need to make some room first. And okay, now there's the different representation. Again, on the left are two triangulations from before. And in the middle, it's the same two triangulations, just drawn with our linear, with our different way to embed them. And as said, the first step is to make some room for the target edges. And one way to do this is the following. So in convex point sets, it's quite nice. Two edges intersect if their points appear in an alternating fashion along the boundary. So here this orange edge and this green edge would cross because the vertices appear in this alternating order. But performing this diagonal flip, which looks like this shift right here, actually moves this to the side, and now this orange edge no longer crosses these edges right here. And we can do this one by one to get the orange edges to the side. And now none of these orange edges cross any of these green edges. So we have made room to start adding new the target edges. And the first one is this edge right here. The quadrilateral is this these arcs right here. So the 2 points that the black edge is connected to right now is this one and this one. The other two are this middle one and the one to the right. So the flip adds this new edge, and it really coincides with one from the target. And we can continue this and add one green edge at a time. So we directly insert these green target edges, really only using one flip per edge. So that's good. And in a final phase, we have made room by putting these orange edges somewhere else. And now it's time to get them to their target position. And finally, we have constructed this triangulation from below with this sequence of flips. And this small example already shows our overall strategy. So in our flip sequence, most edges are going to belong to two groups. I call them with this red E and E prime. So bad edges and good edges, we might call them. And every flip sequence does the following steps. It moves these bad edges somewhere because they might cross some other edges. So it moves them somewhere to make space. Then once we made space, we hopefully have a big group of edges that we now can flip directly to an edge of the target triangulation. And in the last step of the flip sequence, we take all those edges that we have just put to the side to make space and get them also to edges of the target triangulation. So what we see here for these bad edges that we move to the side and move back in later, we spent 2 flips per edge. And for all the good edges, we only spend one single flip. So the mindset that we want to have is we want to make the set of edges that we can flip directly as large as possible and keep the set of edges that we have to flip twice as small as possible. Yeah. And back to this initial example that I gave, the flip sequence that we saw corresponds to what I've drawn on the right. We pushed these orange edges away to make space and then flipped the green edges directly. These triangulations were somewhat symmetric, so what we could also have done is flipping the green edges to the side and flipping the orange edges in directly, and there should be equally many green and orange edges, so both solutions right now are equally good. They are actually the two optimal, or two of the optimal solutions, and they correspond. What we want is that they correspond to two truth assignments to the variable that they have to represent. So orange to the side and flipping green directly is what corresponds to the variable being set to true, and making room by moving the green edges and flipping the orange edges directly is what corresponds to the variable, the corresponding one being set to false. And since everything is going to get quite big on the next couple of slides, one way that will be very helpful to keep track of all these decisions between making space and flipping directly. To track this, we use such conflict graphs that say, well, we have this edge between green and orange. If they conflict, so we have to move green away to flip orange directly, and we have to move orange away to flip green directly. So there's some choice to make between the two. And yeah, that's the variables. Now to the clauses. Every clause connects two variables. So we have the two variables from before right here. And now let's make some space to add clauses in there. And this is going to be a positive clause between two, with two literals that correspond to the positive version of a variable. So it's going to be in the top part. And we add edges like this. And let's look at everything that's going on right here. We have already seen on the previous slide, for every part here, green and orange here, green and orange here, we have to make a decision because we cannot flip the orange edges and the green edges both directly to the target position. We need to move one or the other to the side. And it turns out we can make similar comparisons with the new edges that we just added. It's already depicted here in the conflict graph. And let's look at it also in the drawing of the triangulation. Remember, edges cross if the vertices of the two edges appear in alternating order along the boundary. Or in this case, you can also imagine if we fold the lower part upwards and the two edges would cross, then they really cross. And if you imagine it either way, you see the purple target edges, or maybe it's blue, I don't know how well the resolution for the colors works out. They cross the orange starting edges, so we cannot add purple edges without removing the orange edges. And similarly, we cannot add the orange target edges without removing the purple starting edges. So the same way as we've seen before, before we have seen this double conflict between orange and green, but actually we also, have something like that between purple and orange. And if we look to the right, we have the same thing with red and orange. So the red target edges are crossed by the orange starting edges. The orange target edges are crossed by the red starting edges. So we need to make space by either moving orange or red in order to just have a chance to flip the other one directly. So this also gives this double conflict right here. And one final double conflict is between the purple and the red edges. So again, the same idea. We cannot add the red target edges without moving the purple edges to the side. We cannot add the purple target edges without moving the red edges to the side. And therefore also get this double conflict right here. And this is all the double conflicts that we can observe in here. And now this is where all the details are hidden for this proof then. So one thing is any independent set in this conflict graph right here. So independent meaning if one vertex is in there, none of its neighbors can be in there. So this really gives us a set of vertices such that no two vertices have a double conflict with one another. This really gives us a set of a collection of edges that we can flip directly in a flip sequence between the two triangulations. And on the other hand, if we have conflicts, then we really have to invest some flips to get one part of the edges out of the way, and before we can start adding edges directly to the target triangulation. And if we have more such conflicts in different parts of the triangulations, then these the additional flips that we get really behave additively and they add up in total. So the strategy that we have now is find large independent sets in this conflict graph, as they give us a large collection of edges that can be flipped directly in a flip sequence. And really all the dependencies that we have here really add up negatively for the flip distance, so make the flip distance longer. And we have shifted the problem to finding independent sets in this conflict graph. And now let me show you that this really encodes the behavior of such an OR operator in a clause by going through all the cases. Recall flipping orange directly corresponded to the variables being set to 0. And with those two orange vertices right here, we see in this conflict graph, we cannot add any other vertex to it without getting a double conflict. If instead we replace one of the orange vertices with a green one, then suddenly up here, we made room to also add the purple vertex, and we can add an additional vertex to our independent set. We can also do it the other way around, setting this to 0, this to 1, and add the red one. And what should also be allowed is both vertices here being green, so both variables being set to 1. Then also this clause evaluates to 1. So now red is not in conflict with orange, purple is not in conflict with orange. So we can add either of the two, but not both of them at the same time, because then we have the double conflict between red and purple. And so even if the clause is satisfied by both variables, we can just add one of the two vertices in this conflict graph to the independent set. So going back to the triangulations, even if we choose the right flip sequence for both the variable parts of the triangulation, we can just flip one of the two, either the purple edges or the red edges directly. And therefore, by counting these purple and red vertices in the independent set, we really count the number of satisfied clauses.
Very nice.
Of course,
I do
sorry?
have to say that that is the prettiest slide we had all semester. It's very the color. It's very, very clear. Okay, go. Sorry.
Yeah, of course, there's not only the positive clauses, but also the negative ones. So here's the symmetric construction, and with the conflict graph right here, we immediately see what's going on here. So now this is encoded at the bottom. And yeah, this comes out when we put this entire formula up here together and place every edge the way we just described. And we're almost done right there. Not quite. There might be faces like this that are a little bigger than expected. So this is not yet a triangulation. With the right analysis, it turns out that we can add an arbitrary edge to just compensate for this and actually get the triangulation. Now with this additional edge, both faces have 3 corners and we're happy again. Okay, this is now all the different representations that we've seen so far collected in one slide. We have this initial two-sat formula with its nice representation. Here is what we get when we place all the edges as semicircles the way I described it. Going back to the way we are used to having them, here's the two triangulations in a convex polygon. Yeah, not the same, but here's the starting one and the target one. And one conflict graph once we have all the clauses put in there. And there we really see why it's important to make good decisions, because a bad choice for a variable might not just block one, but multiple clauses. So this really propagates. Yeah. So yeah, that's probably all the different representations that we've seen so far. They look different, but I hope I could convince you that they are actually the same problem. And yeah, one final result. So what we have seen so far is shortest path, finding shortest paths in the Associahedron. I've just shown this is hard to solve. In an earlier stage, we have seen shortest paths in the Permutohedron. That's easy to solve in terms of P and NP. And as I found out only recently, there's something called the Permutoassociahedron that combines the two. So we have the permutations, and on top of these permutations, we then put this association, and there's two ways to transform it now. One way is to make this Associahedron move, so make a reassociation of the elements, and there's also the move for permutations, so we can exchange two consecutive elements if they are not separated by any parentheses. And so this combines something. So how hard is the shortest path problem here? It combines something that's hard to solve, something that's easy to solve. And yeah, this is ongoing work right now. One would expect that the difficulties of the shortest path problem somehow behave additively, and that's also true here. So finding shortest paths here in the Permutoassociahedron is also NP-complete, and this can actually be reduced to what we've seen so far. It uses what I like to call the happy permutation property. So if the starting structure and the final structure are both associations of the same permutation, then any shortest path or any shortest reconfiguration path between the two also only does these bracket moves and none of the permutation moves. So we somehow isolated this hard shortest path problem from the Associahedron. And if we could solve this shortest path problem for the Permutoassociahedron, we could also solve it for the Associahedron. There it's hard, so it's also hard in this mixed case. And actually, this was my final content slide. I only took a little longer than expected, so thanks for your attention.
It was perfect. Everyone, let's thank our speaker. Anyways, questions, unhappiness, discussion. Anyway, I have to say it was very clear. You're getting claps. Anyways, any questions? Okay, what this all has to do with the coherence theory has to be worked out. And I just want to say there's a nice little paper. I don't remember by who. It's like 3 pages or 4 pages connecting all three. There's maps from the Permutohedron to the Associahedron to the Permutoassociahedron and then one generation lower and lower. So they're all like a long exact sequence. Anyways, Peter, fire away. Ask a question.
Hello, can you hear me?
Perfectly.
Yes.
Oh, good. Okay. So first of all, thank you very much, Joseph. That was a lovely talk, and it's also a lovely result. So you didn't actually mention category theory at all, and that doesn't matter because I think it's sort of quite obvious to most people here probably everybody here, how this relates to categorical coherence. Would you agree with that, Russell?
Yes, it's definitely, well, I mean, the Associahedron definitely does. I mean, okay, but we're always looking at the Associahedron is somehow the freest thing. The question is, if we clap certain edges, does it become, P versus as opposed to NP?
Yeah, that's a fair issue. So my sort of big thing essentially is that I consider that a lot of structures in mathematics and computer science and similar are just sort of disguised forms of coherence. So disguised forms of associativity, rebracketing, symmetry, all that kind of thing. So I sort of talked and published a lot about that, and things like group theory, number theory, cryptography, quantum computing and field theory, all that kind of stuff. We get precisely these structures disguised in various different forms. And the neat thing about your results is essentially that when we see NP completeness in one of these settings, we can very directly translate it into NP completeness in any of the other of these settings. So just wanted to say that I've sent in a submission to Logic in Computer Science, the Structure Meets Power conference, essentially talking about the consequences of your work and where we can find NP completeness, particularly in number theory and group theory, where it hasn't been observed before. So I do have one question, as well as just sort of rambling a bit. So
Peter, will that talk be broadcast or recorded or your talk?
I hope so. If not, I can sort of pass on slides, do it at a different point, that kind of thing.
Because I'd love to send out an email with that talk.
Okay, fair enough, fair enough.
Okay.
So the concrete question I have is, I'm used to the Associahedron, not just with the vertices of it defined by binary planar trees, but with all of the facets defined by more general rooted planar trees. So essentially dissections of polyhedra rather than triangulations of polyhedra. So do you have any feeling whether a similar result would apply if we look at, say, edges of Associahedra complete with an adjacency relationship and the shortest distance between different, say, edges or different faces or different volumes of the Associahedron?
So how exactly would this incidence relation look like then?
It would just be the standard sort of description of the Associahedron as a polytope. So adjacency defines in the sort of topological sense.
Okay, so a face is then having all but two edges in common and two faces. So we can move from one, like so in this drawing down here with the hexagon, and we can move from one to the other if they in the dual they share this they share an edge. If they
Yes,
share an
that's
edge
right.
of the Associahedron.
Yeah.
And wow, great question. So this example down here seems to be a little small because if we look at the very left and the very right vertex, then they are completely edge disjoint, but they are both part of a pentagon that would be connected uh, under such a move. I'm actually studying something probably similar. So are you familiar with cosmohedra, where
Oh,
you
yeah.
take
Yes.
triangulations and on top you have this matrushka structure, and you can either flip an edge or shift this like uh, yeah quadrilateral on somewhere else, or such a Matrushka structure on top. And today and yesterday I tried to figure out whether for this case my results can be carried over, and so far it looks good. So it seems that moving bigger things can indeed also be shown to be hard by similar techniques. So I'd have to look into this probably with a bigger example, because I don't see too much structure in this small example right here, but I'd be happy to find out if this works.
Okay. Can I send you something on a sort of number theoretic labeling of Associahedra? Essentially labeling the facets by modulo classes. That will sort of
Yes, please.
explain why this should be quite important, I believe.
Joseph, we should force you to give a talk on the cosmohedra for non-physicists.
Yeah.
That would be a nice
Okay.
thing.
Okay, well, thank you very much anyway. That was lovely. And I shall email you something, and hopefully there'll
Yes,
be some
please.
lots of interesting comment.
Looking forward to hearing from you.
Okay.
Cheers.
If there are no more questions, let's thank the speaker again. And thank you very much, Joseph. We'll be in touch. There is another talk in 2 weeks. Joseph Helfer is talking in person, I believe, and we're looking forward to that. Right, Joseph. Okay, thank you. Ladies and gentlemen, have a wonderful day or evening, depending where you are. And thank you very much. And we will talk. Take care.